Episode 51, titled Link Aggregation, Capacity, Redundancy, and Failure Behavior. The goal is to make link aggregation feel less like a networking trivia topic and more like a practical design tool for speed and resilience. Link aggregation is often described as more bandwidth, but the exam tests whether you understand how that bandwidth is actually realized and what happens when things break. In hybrid networks and data center designs, aggregated links show up everywhere, from server connections to switch interconnects to core uplinks. The key is to understand what the bundle looks like logically, how traffic is distributed across member links, and what failure behavior looks like in real time. When you have that mental model, you can reason about capacity gains, redundancy outcomes, and common pitfalls without guessing. This episode translates the concept into predictable behavior you can explain and troubleshoot. Before we continue, a quick note: this audio course is a companion to the CloudNet X books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. At its core, link aggregation creates one logical link across multiple physical cables, presenting them to the network as a single combined interface. The physical reality is still multiple separate connections, but the logical representation is a bundle that higher layers treat as one path. This matters because routing and switching decisions can then consider the bundle as a single adjacency rather than juggling multiple parallel links independently. Administrators use this approach to increase potential throughput and to reduce the likelihood that a single cable failure causes an outage. The exam frequently frames this as bundling for capacity and redundancy, and the correct understanding is that both are true, but with constraints. The logical link abstraction also simplifies some operational tasks because policies and interface settings can be applied to the bundle rather than repeated across separate standalone ports. The concept is straightforward, but the behavior is driven by how traffic is mapped onto the physical members. Traffic distribution in a link aggregation bundle is usually controlled by hashing, which is the mechanism that decides which flow uses which member link. A hash function takes values from packet or flow headers, such as source and destination addresses, and produces a result that maps the flow to a particular member link. The intent is to keep a given flow on a consistent member link so packets arrive in order, because packet reordering can cause performance issues from many protocols. This explains why link aggregation is not a simple spray every packet across all links model, because spraying packets would risk reordering and jitter. Hashing creates stability per flow, but that stability also introduces unevenness when traffic patterns are not balanced. The exam tends to test whether you recognize hashing as the distribution mechanism because it underpins why capacity gains may look different than expected. When you understand the hash, you can explain why some members are busier than others, even in an aggregated bundle. The distinction between per-flow capacity and aggregate throughput across flows is one of the most important exam points for link aggregation. A single flow typically uses only one member link because the hashing decision pins it to that member to preserve ordering. That means the maximum throughput for a single flow is often limited to the speed of one physical link, even if the bundle contains multiple links. The bundle increases total capacity by allowing multiple flows to be spread across different members, so the aggregate across many flows can approach the sum of member capacities. This is why link aggregation helps most when traffic consists of many independent flows, such as many clients accessing a service or many simultaneous sessions between systems. It is also why a single large transfer may still be capped, because it may be one flow that cannot exceed one member's speed. The exam often tests this by describing a single transfer that fails to reach expected combined throughput and asking what explains it. The correct reasoning is to separate total available across flows from what one flow can use. Redundancy behavior is where link aggregation becomes a resilience tool, because the bundle can continue operating when one member fails unexpectedly. If a cable is cut, a transceiver dies, or a port drops, the aggregation logic removes the failed member from the bundle and continues forwarding using the remaining members. Existing flows that were mapped to the failed member may experience a brief disruption as they are remapped, but the bundle does not necessarily collapse entirely. The recovery behavior depends on detection speed and how quickly the endpoints agree on the new member set. In well-designed environments, this failover is quick enough that many applications see only minor impact, such as a short pause or a retry. The exam expects you to understand that the bundle is resilient but not magical, because failures can still cause transient loss. The important point is that redundancy is achieved by having multiple independent physical links under one logical interface, so one failure does not eliminate connectivity. Link aggregation is commonly used between switches, between servers and switches, and on core uplinks where both capacity and redundancy matter. Between switches, aggregation provides higher throughput for interswitch traffic and prevents a single physical link from becoming a bottleneck. Between servers and switches, aggregation can improve availability for server connectivity and can increase aggregate throughput for workloads that use many parallel sessions. On core uplinks, aggregation helps prevent the core from being constrained by one link and provides a safety net if one uplink fails. The exam may describe these environments in general terms, and you should recognize that aggregation is most valuable where there are multiple independent flows and where link failure would be operationally painful. It is also often used to avoid designs that rely on a single physical link in a critical path. The key is that aggregation is a building block, not a full architecture, and it must fit the topology's redundancy goals. When it is placed appropriately, it reduces both bottlenecks and outage risk. A capacity scenario that illustrates link aggregation well is when a single uplink saturates during backups, causing slowdowns or timeouts across the environment. Backups can generate large volumes of traffic, often involving many parallel connections from multiple servers to backup targets. If those flows are forced through one physical uplink, that link can become saturated, increasing latency and packet loss for other traffic sharing the same path. Aggregating uplinks can increase total available throughput so that backup traffic is distributed across multiple members, reducing the chance of a single link becoming the choke point. This works best when backup traffic consists of multiple flows, because hashing can then spread those flows across members. The scenario also highlights that the improvement may not be visible if the backup process uses one large flow, because that flow will still be capped by one member's speed. On the exam, when backups saturate a link, aggregation is often a plausible mitigation, but you must still reason about flow behavior. The tested understanding is that aggregation helps the aggregate problem, not necessarily the single flow problem. A redundancy scenario is when one cable fails but service must continue, such as a server connection that cannot drop because it supports critical workloads. With link aggregation, the server can remain connected through the surviving member links, and the switch sees the bundle as still up. From the application viewpoint, this can look like a brief hiccup rather than a full outage, assuming higher layer protocols handle transient loss gracefully. This design is especially useful for connections where physical failure risk is non-trivial, such as cables that run through crowded racks or links that are frequently moved during maintenance. The bundle provides a form of resilience that is simpler than maintaining separate, independent network paths at higher layers. The exam often frames this as one link fails, connectivity continues, and link aggregation is a direct match to that requirement. The important nuance is that resilience depends on correct configuration and proper detection, not just on having extra cables. Uneven hashing is a common pitfall, and it can cause one member link to be overloaded while others remain underused. This happens when traffic patterns are skewed, such as many flows sharing the same source and destination addresses, or when the hash inputs are too limited to distribute traffic evenly. For example, if the hash considers only certain header fields, two large flows might collide onto the same member link, saturating it while other members sit idle. This can create confusing symptoms where the bundle appears to have plenty of capacity overall, yet performance is poor because one member is the true bottleneck. The exam tests this by describing an aggregated link where utilization is uneven and asking what explains the slowdown. The correct answer is not that aggregation is broken, but that hashing distribution is imperfect given the observed flow characteristics. Understanding this pitfall also helps you choose better hash policies and to interpret member-level utilization data correctly. Mismatched configuration is another serious pitfall, and it can create loops or black holes that are far worse than simple performance loss. Link aggregation requires both ends to agree on how the bundle is formed, which members belong to it, and what negotiation settings are used. If one side believes a link is part of the bundle and the other side treats it as a standalone port, traffic can be misforwarded, duplicated, or dropped. Loops can form if the topology unintentionally creates parallel forwarding paths that the switching logic does not expect, leading to broadcast storms and widespread disruption. Black holes can occur when traffic is sent down a member that is not actually forwarding as part of the bundle on the far end, causing silent drops. The exam often tests this by describing intermittent connectivity, strange spanning tree behavior, or sudden network instability after configuration changes. The key is that link aggregation is a coordination problem between devices, and mismatches create unpredictable outcomes. Correct, consistent configuration on both ends is a non-negotiable requirement. Quick wins for stable link aggregation start with standardizing settings and monitoring member utilization consistently. Standardization means using consistent bundle definitions, member counts, negotiation settings, and hash policies across similar connections so troubleshooting does not become a one-off puzzle every time. Monitoring member utilization matters because the bundle-level view can hide uneven distribution, while member-level metrics reveal whether hashing is spreading traffic effectively. You also want alerts for member failures so you know when the bundle has lost redundancy and is operating on reduced capacity. Monitoring should include error counters and drop rates because a member link can remain up while performing poorly due to physical issues. These quick wins support both performance and resilience because they help you detect drift and failures before they become outages. The exam expects you to treat monitoring as part of the design, not as an optional add-on after problems appear. When you can speak to both configuration discipline and visibility, you show an operational understanding that aligns with real-world practice. A useful memory anchor is bundle, hash, monitor, fail gracefully, because it captures the essential mechanics and the operational posture. Bundle reminds you that the logical link is built from multiple physical members that must be treated as a set. Hash reminds you that flows are assigned to members based on a deterministic selection mechanism which drives capacity behavior. Monitor reminds you that performance and resilience depend on visibility into member utilization, failures, and errors, not just bundle status. Fail gracefully reminds you that redundancy is about continuing operation through member failure, accepting that some flows may reset or pause, but service should continue. This anchor helps you reason through exam questions quickly because it aligns with the most common tested issues: distribution, capacity expectations, and failure handling. When you can explain each word in the anchor, you can explain link aggregation without getting lost in implementation details. To apply the concepts, imagine being asked to diagnose a slow link even though aggregated capacity should be high. Your first thought should be whether the workload is dominated by a single flow, because per-flow capacity is usually limited to one member link regardless of bundle size. Your second thought should be whether hashing is uneven, causing a small number of heavy flows to collide on one member while others remain underutilized. Your third thought should be whether a member has failed or is erroring, reducing effective capacity and forcing more traffic onto fewer links. You should also consider whether configuration mismatch is causing drops or misforwarding, because that can look like random slowness. The exam expects you to follow this reasoning rather than to assume that aggregation automatically multiplies speed for every traffic pattern. When you can connect observed symptoms to flow behavior, hashing, and member health, you demonstrate true mastery of the topic. To close episode 51, titled Link Aggregation, Capacity, Redundancy, and Failure Behavior, the core idea is that link aggregation creates one logical link from multiple physical links to increase aggregate throughput and to provide redundancy when a member fails. Hashing determines which flow uses which member, which explains why a single flow usually cannot exceed the speed of one member, even though many flows can collectively use the bundle's full capacity. When a member fails unexpectedly, the bundle can continue operating on remaining members, preserving connectivity with only transient disruption for affected flows. The pitfalls are predictable, including uneven hashing that overloads one member and mismatched configurations that create loops or black holes. Standardized settings and member-level monitoring are quick wins that keep bundles reliable and make performance issues diagnosable. Your rehearsal assignment is to explain link aggregation to an imaginary colleague in one pass, explicitly stating the per-flow versus aggregate capacity rule and the member failure behavior, because that explanation is exactly what the exam expects you to understand and apply. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.